Hey, what's up, guys? This is Sheng here. So today, number 1761, minimum degree of a connected trio in a graph. So you're given like an undirected graph, right? And then you have an integer n and the and the list of edges for the graph, and you need to find all the connected trio, which is a set of three nodes where each node is connected to each other. Basically, you need to find like a size of three strong connected graph, right? And then for each of the strong connected three size three graph here, you need to find the degree of that. So the degree of that is basically is the edges, right? That's not belong to this strong connected graph itself, right? So for example here, so we have a trio, right, which is a 1, 2, and 3, right? Because those three are connected to each other, and the degree for this trio is like 3. Basically, anything that's we remove the connected edges inside, and then all the rest will be the final answer. That's why the answer is 3. Okay, and we need to find the minimum degree. Basically, we need to find all the possible trio, right, in this graph, and we just need to get the minimum degree among all of them. And remember, so the graph it may not be a connected graph, right? So for example, this one, right? The we have a trio here. So this one, the degree for this one is obviously 0, and on the right side, we have two trio. Basically, we have 2, 4, 7. Sorry, we have 2, 5, 6, and 5, 6, 7. And either of those two trio have degree of 2, right? So for example, we have 2, 5, and 6. So the degree is like this one and this one. That's why the degree is 2. And the range is like the size of this n is like 400, and yeah, and that's it, right? So the edges will be like the within this range. Cool. So I mean, so for this problem, I mean the intuition is pretty straightforward. Basically, at the beginning, we just create a graph, right? We create a graph, undirected graph here, and then we just for each of the node here, we'll try to find the trio that includes the current node, right? So the way we're doing it, we can simply do a nested for loop here. So for each of the each of the node, right? So we try all the possible all the possible neighbors for this current node here. For example, if we have the one has like 3 nodes, right? We have 2, 3, and 4. Basically, we try all the combinations of those two of the neighbors, and then if those basically the current one is not num1, right? So we have a the current one is node 1, and then we'll try to find all the combinations of node 2 and node 3, right? Among all the node 1's neighbors, and then among all those each of the combinations here, we check if basically if n2 is in the range is the neighbor of n3, which means that if there's a like graph, right? So if the n2 is in the if it is a neighbor of n3, then we know, okay, so we have a like a trio, right? Because since the n2 and is a neighbor of both n2 and n3 are the neighbors, neighbor of n1, right? And then if n2 and n3 is neighbor, then we find the trio. Okay. So yeah, I think that's a pretty straightforward, right? And let's try to implement that. But the problem with that approach is that for this problem, it will TLE. I think that's why this one got a lot of downvotes, because It's simply just TLE. Yeah. So we have default, right? Default dictionary as set. Okay, I'll just do it. And then we have for.uv in edges, right? And then we just create a graph of u and v. So I'm just implementing the first approach just to show you guys the idea, and then we'll try to improve a little bit on that so that we can overcome that TLE. So now we have a graph, right? We have undirected graph here, and for n1 in range of 1 to n plus 1, right? So for each of the node, we're gonna basically enumerate all its neighbors, the combinations of the neighbors, by selecting n2 in graph of n1, and then for n3 in graph of n1. Okay, and if n3 is in the graph of is a neighbor of n2, you can also do a n2 is a neighbor of is in the graph of n3. Either one works fine, right? And then we just have like this answer equals to minimum of the answer dot what? We have a length of the so once we have find 3 nodes here, right? We just need to accumulate all the degrees, right? All the degrees for those 3 nodes here, and then we just do in the end we subtract 6 because we have 3 edges. Basically we have 6 edges. So this one has 2 edges. This one else has 2. This one has 2. We just need to subtract the 6 out of the total degrees, and then we have our answer. So here, I mean it's going to be a length of n1, right? Plus length of graph dot n2 plus length of the graph of n3, right? And then we in the end we subtract 6 and then return, right? Else minus 1. Yeah. So this one will work basically, But if we submit it, you'll see it will TLE. Yeah. So I don't know. It TLCs in a way because for some reason, right? It's just like I think the main reason it TLE this time out is because we're duplicating we're double counting those trails multiple times, right? For example, if we have 1 2 1 2 3, we may have 2 1 3, and then we may have 3 2 1. Basically, since these edges are undirected, right? So that's why we're gonna basically calculate each trail multiple times. So so how can we improve that, right? How can we only calculate that trail once, trail once, right? So the trick for this problem is that we can convert this undirected graph to a directed graph so that we'll remove the edges by half, right? So in that case, when we loop through the those two for loops here, we will basically cut the total for loop by half. Okay, and how can we convert this undirected graph to a directed graph, right? I mean, we cannot simply do this, right? I mean, if we do it in this way, basically there will be an issue. The reason being is that it has to be a graph that without like a circle. Otherwise, we'll have an issue. For example, we have 1 2 3, right? So we have 1 2 and 3. So it cannot have a circle. Basically, if this is the edges we're building here, right? So this is a circle, right? If we only just blindly do this u to v here, in case we have like a circle here, this one will not work. Basically, will not find this this trail, because no matter which node we choose here, right? If we choose 1 here, we'll not have. So basically, we'll only find either 2 or 3. We'll not find 2 neighbors. That's why, so we will not find 2 and 3 at the same time. So which means that it cannot be a like circle. So how can we make sure the graph doesn't have a circle? We can make a rule here. So the edge is always pointing from the smaller number to the bigger number. So in that case, we're gonna have like this one, right? So in this case, we'll have this one. We have 1, 2, 1, 3, and 2, 3. In this case, this is not like a circle, so that we can make sure we'll always find the trail. Because, for example, of course, when you loop 2 here, you will not find the trail. But when you are at this 1 here, we have 2 neighbors, right? So we have 2 and 3, and then since we are like looping through all the possible combinations, right? So basically, so this one could be 2, this one could be 3, right? So in this case, 3 is in the like neighbor of 2, right? On the other side, right? So this one can be a 2 and 3, right? Since we have a full for loop here. That's why we can just only need to check this one once. And we don't need to worry about n2 of n3, because there will always be the case that we have loop through. We have the number 2 is 2, and the n3 is 3. So we can only do this one if check here, right? So yeah, but since we also need to do this kind of like degrees in the final calculations, and since we have already cut the edges by half, right? So if we're still using this like the length of the graph here, we'll not get the correct answer. So that's why we're gonna have like another degree dictionary here. So default dictionary dot int, right? So then we always pointing from the smaller number to the bigger number, right? So it's gonna be this one, and then max of u and v. And for the degree, right, we have u plus 1, degree of v plus 1. Cool. So now we can just do this, right? Degree of this, this, and this. Yep. So if we run the code again, oh, okay. So then it's not, we don't need this length anymore. Okay. Accept it. So submit. Okay, cool. So this time it's passed, right? Because basically we cut the runtime, the time complexity by half, by only maintaining one edge between 2 nodes, right? So that we can reduce the for loops here. But still, right? So the time complexity for this problem is still n cube, right? Because we have this kind of nested for loop here. Yep. So I think that's it, right? So the idea is pretty straightforward. The tricky part is that how can we somehow reduce the time complexity, the runtime for this. Basically, we are, instead of building a undirected graph here, we're building like a directed graph. But we cannot blindly assign the edge from one to another. We have to make sure there's no circle in this graph. Okay, that's why we're making a rule here. We're always building the edge from a smaller node to a bigger node. In that way, we can make sure, we can guarantee that there's no circle. And the rest is pretty much the same. Yep, I guess I'll just stop here, and thank you for watching this video, guys. Stay tuned. See you guys soon. Bye-bye.